This video will discuss all 13 active volcanoes within the state of Oregon, even the lesser known ones, with each volcano and their last eruptions being discussed beginning at their timestamps shown on screen. Enjoy! When most people hear the term shield volcano, they think of a broad and gentle slope volcano often covered with fresh black lava in either the Hawaiian island chain or the Galapagos Islands. Yet, despite typically being associated with very far away places, it might surprise people that the state of Oregon also contains not only a shield volcano, but one which is considered still active. The shield volcano I'm referring to can be found 30 miles west-northwest of the city of Bend, and already from satellite you can see a near-perfect circular region spanning 6.2 miles wide, which is covered in fresh-looking lava flows. This represents the Belknap Crater shield volcano, which completely formed in the last 10,000 years. If you were to have only been in this very spot 1500 years ago, you would have witnessed spectacular lava fountains emanating from its summit cinder cone, which slowly but surely created a bright orange glow as it flowed downhill to the south. While Belknap Crater might be thought of as a fluke or rarity of sorts in the region, this is not the case. The Oregon portion of the Cascade Range has produced at least 4 Belknap Crater-like shield volcanoes in the last 500,000 years, of which Belknap Crater just happens to be the most recent. Yet, while Belknap Crater is the singular volcano, it challenges the notion of being a typical shield volcano, as while many famous shield volcanoes erupt from the same central vent multiple times, Belknap Crater never did this. Instead, Belknap Crater could best be thought of as the combination of several distant moderately explosive to effusive eruptions which, when combined, formed a shield-like structure. Its central cone might look truly uniform at first, but in reality is the combination of 2 separate small-scale shield volcanoes in addition to 2 small flank vents. In other words, no vent erupts twice at this volcano, and Belknap as a whole is considered monogenetic. The first eruption of Belknap Crater occurred 4 miles northwest of its modern summit. As low silica basaltic magma intruded into the crust approximately 9,500 years ago, it generated a series of earthquakes. Soon, persistent rumbling became audible until finally the expansion of gases propelled the magma upwards, causing it to break through the southwestern slope of the extinct Mount Washington shield volcano and erupt via a 500-foot-tall fountain of lava. Within a few minutes, an underlying dike of magma also reached the surface in 6 additional locations to the south, meaning lava was now erupting along a 9,500-foot-long stretch of land. Intermittent explosions subsequently began which created ash, and these combined with falling bombs of lava to create a series of cinder cones. As lava erupted at a high rate, numerous lobes of lava created sounds similar to glass breaking and advanced at a slow speed of up to 50 feet an hour towards the west. By the time this 3.5-week-long eruption ended, approximately 4 square miles had been covered in lava via what are today called the inaccessible cones. The next eruption from this complex occurred around 5050 BCE, but this time did not have a mildly explosive component to it. Shorter fountains of lava were still generated, but instead a short spatter cone breach towards the west was constructed, which fed the Tamaliche lava flow that would travel 4.5 miles to the southwest. Before the next eruption, the magma chamber of Belknap Crater underwent fractional crystallization, causing its magma composition to change from basalt to basaltic andesite. A nearly 2-decade-long eruption followed in 900 BCE, where a central vent overflowed its pit crater and sent lava flows in all directions at a rate of about 7 cubic meters per second. This eruption would have been spectacular to watch and formed the Little Belknap Shield volcano. The next eruption occurred around the year 0, creating a 1 square mile lava flow on Belknap's southern flank. 300 years later, a moderately explosive eruption occurred at 2 simultaneous vents where the twin craters and South Belknap cinder cones erupted for a period of several months. Belknap's last eruption happened to be its largest, where for a period of several decades a moderately explosive eruption built a central cinder cone which effused layer after layer of basaltic andesite lava primarily towards the west. By the eruption's end, a peak now stood 2,000 feet higher than what used to be much lower topography in the same spot only 10,000 years prior. Today, it is assumed that Belknap crater as a shield volcano will never erupt again since its vents are monogenetic. However, there is still a low probability potential for new vents to one day pop up within an up to 7-mile radius of this fascinating shield volcano. Such future eruptions will be most likely completely effusive to moderately explosive, albeit remote, with the potential to disrupt regional air traffic or have lava potentially flow onto Route 126 or Route 242. As a result of these hazards, the U.S. Geological Survey designated Belknap crater as a low-threat volcano. About a millennia ago, a powerful explosive volcanic eruption occurred in the state of Oregon, hurling boulders of rock up to a mile away. As a thick plume of ash rose into the atmosphere, superheated pyroclastic flows incinerated a square-mile of forest, starting a wildfire. Then, abundances of ash began to fall, and over the next several hours, an area of 16 square miles will receive 10 or more inches of ash. Such a total in the modern day would be more than sufficient to collapse building roofs. What I just described did not occur at a towering peak seen from afar such as the Three Sisters or Mount Hood, but rather a largely hidden volcano which few are aware of. Known as the Blue Lake crater after its namesake crater lake called the Blue Lake. This lake marks the interior of an overlapping series of volcanic explosion craters which are termed Mars. This is the story of a largely unknown volcano which is considered to be one of the planet's smallest active volcanoes and may one day erupt again. The volcanic complex known as Blue Lake Crater is located within a 150 square mile area of central Oregon, which since the end of the last ice age has been an epicenter of largely effusive to moderately explosive cinder cone forming eruptions of a basalt to andesite composition. Despite lower silica content lavas found at the Blue Lake Crater which are basaltic, generally being less explosive, the interaction with significant groundwater will always be violent and highly explosive regardless of the type of magma which interacts with it. Such highly explosive eruptions of nearly identical composition lava has occurred, for example, at the Kilauea volcano such as in 1790, despite Kilauea being primarily known for its magnificent effusive eruptions. Despite its name, the Blue Lake crater does not merely contain the 2,900-foot-wide explosion crater which goes by the same name. As on the northeastern flanks of the extinct Mount Washington Shield volcano, there is a cluster of small volcanic vents which stand out in the highly eroded landscape. There, across a 4,500-foot-long stretch of land, there are 13 small spatter cones present which are also part of the Blue Lake Crater volcanic complex. These vents perfectly align with the trend of the 4 explosion craters which comprise Blue Lake and also have the same composition of eruptive products. In other words, they all formed in a single eruption. This trend represents a single, now solidified, approximately 4.6-mile-long magma dike somewhat like we have recently witnessed on Iceland's Reykjanes Peninsula. This dike formed in the year 665 CE when an intrusion of magma occurred which quickly reached shallow depths in the crust. Perhaps due to a layer of hardened ancient igneous rock, this dike branched off into 2 segments with one at each end. As magma progressed upwards, large cracks developed in the ground which continued to spread apart. Several explosions occurred, and as ash was ejected from 3 small fissures, a series of small lava fountains emerged. These fountains quickly died down, giving way to the intermittent and weak ejection of lava which built a series of 13 small prominent spatter cones. Then, 4¼ miles to the north, magma reached the surface of a low-lying lake, causing the groundwater beneath it to flash to steam, build in pressure, and violently explode upwards. As a plume of ash shot 20,000 feet into the sky, ejected heavier materials including large boulders fell back to the ground along with gas, generating pyroclastic flows which scorched the landscape in a radius of 0.6 of a mile. This first explosion formed what is known as a maar which was 200 feet deep and 1,600 feet wide. Then, another powerful explosion occurred, forming a second large crater to the northeast. This process occurred 2 more times, leading to the creation of a complex maar explosion crater. After the southwestern fissure-based spatter cones ceased their activity, small amounts of lava erupted from the now evaporated lake, creating a brief lava fountain and adding cinder to the surrounding layers of ash. This eruption, the only known to have occurred from this volcano, had a volcanic explosivity index of a 3 and left behind as much as 2 meters or 6.6 feet thick of ash next to the crater lake vents. While it is not a certainty that this complex will ever erupt again, the Mars could now theoretically represent a long-term path of least resistance. This means that a future highly explosive eruption could occur if magma ever intrudes into shallow depths in the vicinity with the lake water still present. However, few people live in direct striking distance of a hypothetical future eruption. As a result of these hazards, the U.S. Geological Survey designated the Blue Lake crater as a low-threat volcano. Looking at the vast deep blue waters of the Crater Lake volcano in Oregon, and noting its up to 2,000-foot high steep walls which stretch across a length of 20.8 miles, you can tell that something truly cataclysmic once occurred here. As this deep depression in the ground which contains the United States' deepest lake did not always used to be here. If you were to have only been in the same spot a mere 7,800 years ago, there would have been a completely different sight. Specifically, you would have witnessed a towering glacier-covered stratovolcano which reached an impressive height of 12,000 feet or 3,658 meters, marking it as the tallest peak in the state of Oregon. Much like Mount Adams, this stratovolcano, due to its age, was glacially dissected with numerous large ravines and notable lava flows on its flanks with glaciers on its summit. But a significant hydrothermal alteration on the volcano would reveal all was not well, as the unusually large volume and volatile-rich magma chamber was building at depth. Thick ash deposits from a powerful eruption 100 years earlier cover this volcano's outskirts, although forests had reclaimed the destroyed area. Meanwhile, the thick lava flows that older eruption produced were still steaming. Yet, within a generation, the towering stratovolcano known as Mount Mazama would vanish, having collapsed in only 160 hours' time in the Cascade Range's largest explosive volcanic eruption during the last 1 million years. For context, the Crater Lake volcano can be found in southwest central Oregon, where it is located 55 miles northeast of the city of Medford. Like the vast majority of Oregon's active volcanoes, the Crater Lake volcano exists due to the offshore collision of two tectonic plates in the Pacific Ocean. There, the Juan de Fuca plate is colliding with and subducting underneath the North American plate. The melted material from this collision then migrates upwards, intruding into the crust and occasionally reaching the surface and erupting, forming the Cascade Range volcanoes. The Crater Lake volcano began forming approximately 500,000 years ago when a volume of dacite composition magma erupted onto the surface 5 miles east of what would eventually become the summit of Mount Mazama. This initial eruption was explosive and emplaced a large volume of viscous gray-colored lava flows, building the lava dome complex of Mount Scott. Other smaller volume more anesthetic eruptions occurred from isolated scattered vents occurring across an area of 250 square miles. Over time, these scattered vents became increasingly clustered and moved slowly towards the west until by 410,000 years ago, Mount Mazama proper began to grow. It is around this time that the so-called phantom ship lava was emplaced 400,000 years ago. Over the next 315,000 years, hundreds of lengthy explosive eruptions followed, resulting in the deposition of overlapping layers of lava and ash. These eruptions were for the most part moderately explosive. Yet, over time, Mount Mazama's underlying magma chamber continued to undergo fractional crystallization until large swaths of its magma had a dacite to rhyolitic composition. Around 85,000 years ago, the first warning signs showed as the volcano produced its first Plinian eruption, ejecting 2.4 cubic kilometers of ash. The rate of large eruptions continued to increase over the following tens of thousands of years, and then the second warning sign appeared. As, around 30,000 years ago, two unusually large rhyolite lava flows erupted, emplacing the features known as Grouse Hill and Red Cloud Cliff. Then, in 5900 BCE, another such eruption occurred and formed lava rock, but this time was an order of magnitude more explosive. This eruption was approximately the same size as the 2022 eruption of the Hunga Tonga Hunga Ha'apai volcano in the nation of Tonga, and emplaced rhyolite lava which was in some areas more than 1,000 feet thick. Then, for 117 years, the volcano was eerily quiet. Yet, the number of volcanic earthquakes continued to increase until finally volatile-rich magma and mass pushed upwards through the crust. When Mount Mazama's climactic eruption began in 5783 BCE, you could have been as much as 43.5 miles or 70 kilometers away and still not have been safe. As tens of thousands of tons of volcanic ash per second was ejected to a height of 180,000 feet or 55 kilometers, the plume drifted towards the northeast. Part of the eruption column then collapsed back to the ground, resulting in unusually long-reaching pyroclastic flows that filled valleys with as much as 300 feet thick of superheated material, traveling up to 44 miles distant. All life was extinguished within a 25-mile radius of Mount Mazama, and the eruption was not even over. As much as 15 feet thick of ash fell adjacent to the erupting peak, while 85 miles away what is now the town of Bend received more than a foot thick of ash. Lesser volumes of ash that were enough to remain in the geologic records subsequently fell across 8 US states and 3 Canadian provinces, covering a total area of nearly 2 million square kilometers in ash. Yet, because so much material had been ejected from Crater Lake's underlying magma chamber, it soon became largely empty. This caused large masses of overlying rock to collapse downwards and filled the empty space in this magma chamber, destroying Mount Mazama as it collapsed into a 4,000-foot deep and 6.2-mile-wide caldera. In total, 176 cubic kilometers of tephra was ejected, meaning the eruption was equivalent to 135 simultaneous eruptions of Mount St. Helens in 1980, with Crater Lake's caldera forming event being assigned a Volcanic Explosivity Index of a 7. In the following several hundred years, steaming deposits of pyroclastic flow material remained, while at the same time water began accumulating in Crater Lake, forming a large body of water. This lake would subsequently be the site of 4 additional eruptions, the most notable of which formed the andesitic cinder cone known as Wizard Island atop a massive underwater lava in 5100 BCE. The last eruption of this volcano occurred in 3000 BCE, forming a rhyolitic dome which is currently completely submerged below the waterline. Today, while there are no immediately obvious signs of volcanic activity, the Crater Lake volcano is still very much considered as an active system. While there are no signs that it will erupt anytime soon or the present, it is likely that the Crater Lake volcano will one day erupt again. Due to these hazards and the most recent volcano hazard assessment from the US Geological Survey, the Crater Lake volcano was rated as a very high-threat volcano. Within Oregon, 4 of the state's approximately 400 cinder cones stand out due to their unusual composition, as adjacent to Davis Lake are a series of 4 such cones which, a mere 5,000 years ago, produced unusually massive and tall lava flows which tower up to 315 feet above the tree line and the surrounding landscape. These lava flows are somewhat unusual as the vast majority of cinder cones around the planet primarily produce basalt or basaltic andesite lava flows. As the erupted lava these cones produce increases in silica, the resulting lava flows become more viscous and thus move less far, but become far thicker. If you keep going upwards on this trajectory, you eventually reach such a thickness that the lava would form a cap, causing gas to become trapped underneath it, build in pressure, till finally it generates a series of powerful explosions. These explosions would prevent a cinder cone from ever forming. However, there is a Goldilocks zone where the gas content of a magma is not too high to destroy any cinder cones which grow, but not too low to not cause any form of ash emissions. Along with the Crater Lake volcano's Wizard Island, another cluster of andesitic cinder cones which fell under the Goldilocks zone are the 4 young cinder cones of the Davis Lake volcano. These cones and their associated lava flows are all aligned along a single lineament, suggesting that they all formed at the same time as part of a single volcanic eruption, which was related to an 11-mile-long magma dike. Altogether, these 3 spaced lava flows cover an area of 14.12 square kilometers or 5.45 square miles. These lava flows originated from the flanks of fairly small cinder cones which ranged in height from 150 to 350 feet. And this might be the key why it was even able to form in the first place. I personally estimated that around 18 million cubic meters of tephra and ash is present, a surprisingly small total considering that the relevant eruption produced 420 million cubic meters of andesitic lava. But even for andesitic lava flows, the ones at Davis Lake are still unusually tall. The reason for this is that multiple lava flows were in place during what I estimated to be a 27-day-long eruption, some of which overlapped each other. This overlapping of lava flows is best seen in the middle of the 3 lava fields. The reason these earlier lava flows are more densely forested is that they likely contained a layer of ash owed to more intense ash emissions during the first several days of this 3000 BCE eruption. The lobes of material allow you to easily see what pathways the viscous lava flows took, which likely advanced at a speed of only 50 feet an hour. On flatter terrain, they spread out like an alluvial fan, while, when forced into a narrow channel, the lava increased in height. If you were to have stood in this very location 5,000 years ago, you would have witnessed largely Strombolian activity occurring, with ash emissions occurring alongside intermittent lava fountains and small explosions. The sound of breaking glass would have been heard as the lava slowly crept forward, and occasionally blocks of material would tumble off, sometimes rolling for several hundred feet. While these vents are the youngest features in the Davis Lake volcanic field, they are not the only volcanic features nearby, as the Davis Lake volcanic field has been infrequently erupting for around 610,000 years, with each vent erupting no more than once. This volcanic field also includes 8 small shield volcanoes which all seemingly formed in pairs. Altogether, the exact ages of these basaltic andesite shield volcanoes is uncertain, but I would estimate that they formed around 610,000, 400,000, 200,000, and 50,000 years ago. Due to the low eruptive rate at this active volcanic field and the fact that its eruptions seem to produce only light ash emissions, the U.S. Geological Survey designated the Davis Lake complex as a very low-threat volcano. Within Oregon's scenic Cascade mountain range, there are a wide range of active volcanoes which have erupted in the last 10,000 years. Ranging from the vast Holocene caldera of Crater Lake to the cluster of stratovolcanoes of the Three Sisters to the shield volcano of Belknap Crater, there are a wide variety of features. Yet, it might come as a surprise to some people that the Cascade Range doesn't contain all of the state's volcanoes, as to the east there is a strange province known as the High Lava Plains where, during the last 15,000 years, repeated large outpourings of lava have occurred from multiple complexes, leading to a cluster of black lava fields so large that they are each visible from orbit. The most remarkable of these young lava fields can be found 8 miles northwest of the small community of Diamond, from which it originates, part of its name being known as the Diamond Craters. At this very location, approximately 7,500 years ago, a singular 5-year-long eruption would create everything volcanic you can see, involving both diffusive and explosive activity. This sustained eruption not only led to some areas being buried by more than 300 feet thick of lava, but also by an additional 60 feet thick of ash on top of it. So, why exactly did such a voluminous eruption occur in the 6th millennia BCE? The answer relates to an abnormality regarding the same force driving the volcanoes in the Cascade Range, the subducting Juan de Fuca tectonic plate. Although the exact reason why this occurred is unclear, in geologically recent times a small portion of the Juan de Fuca plate was unexpectedly pulled downwards at a steeper angle. As a result, viscous material in the mantle was quickly forced into the empty space the plate once held, creating a curved motion that pulled molten rock upwards. Fairly sizable volumes of the molten rock pulled upwards by this action subsequently intruded into the crust, some of which eventually erupted, forming the volcanoes of the high lava plains. In the year 5555 BCE, a 3.7-mile-long dike, aka a long and thin body of magma, intruded into the crust, causing cracks to form on the surface paralleling its north-northwest orientation. As a plume of gas emerged from the ground along multiple points, it was only a matter of time before an eruption began. After an initial explosion, lava shot several hundred feet into the air at a point which we now associate with the center of the Diamond Craters complex. Subsequently, the lengthy fissure unzipped in both directions, causing an ever-expanding length of the fissure to be erupting lava at a high rate. This continued until a 15,000-foot-long stretch of ground was erupting lava at a combined rate of upwards of 200 cubic meters per second. As lava poured out, it spilled over in all directions, quickly filling low-lying areas and dozens of feet thick of molten rock and covering areas up to 3 miles away. Yet, as the eruption progressed, parts of the lengthy fissure complex became dominant, first forming a cluster of a half-dozen vents, but as the days progressed, this whittled down to a single central vent. By then, the rate of lava effusion had decreased to around 4 cubic meters per second, eventually causing a complete pause in eruptive activity. As thick lava flows began solidifying on the surface, a few months would follow until unexpectedly a new batch of magma intruded right below the original ground level. As this magma continuously intruded underneath a layer of sedimentary rock, it built in volume and caused the overlying rock to be pushed upwards. This greatly cracked wide swaths of overlying lava, pushing it upwards by as much as 200 feet over a few months to form 6 large domes. The very magma which caused this doming soon approached the surface, where it interacted with groundwater that had developed during the eruption pause. The heat generated by this magma caused patches of groundwater to flash to steam, and since the same massive steam takes up more than 1,000 times the volume of the water it once was, it caused an immense amount of pressure to build. This pressure eventually became sufficient to crack overlying rock, generating a powerful explosion which carved out a several hundred-foot wide crater. Over the following 3 years, this process will repeat 89 more times, forming what are known as maars and causing several feet thick of ash to be dispersed over the surrounding landscape. At the latter stage of this phase, areas which were now groundwater poor became the site of ever-growing cinder cones which ejected bombs of lava over a 1-mile radius in a Strombolian manner and produced intermittent ejections of ash. One such cinder cone that formed during this phase is today known as the Little Red Cone. After these ceased, the underlying shallow magma clustered underneath what was the dominant spatter cone in the original fissure which initially erupted. This magma was unusually volatile and gas-rich when compared to the beginning of the ongoing eruptive sequence. As a result, when this magma rose towards the surface, no lava actually emerged, as instead what used to be lava was pulverized and shattered by the expanding gases, causing a sustained plume of ash to rise to a height of 10,000 feet. Ash from this plume quickly began falling across the surrounding landscape, completely coating the near vent area in several feet thick of ash. At this point, the eruption looks somewhat like the last month of Cumbre Vieja's 2021 eruption, completely coating the nearby landscape in a layer of finely grained ash. Although activity regularly waned and intensified, near-continuous ash emissions likely continued for a period of 3 to 5 months. By the time this central vent shaped like a cinder cone had ceased erupting, as much as 60 feet thick of ash had fallen, although the thickness of ash quickly fell off to only trace amounts beyond a distance of 3 miles. I want to note here that ash may very well have accumulated at more than trace amounts at much further distances than 3 miles away. Just if this was ever true, then this fact was erased from the geologic record via subsequent precipitation. After another brief pause in the eruption, magma migrated to the southeast, east, and northeast, causing the shallow magma chamber to become partially empty. As a result, there was now only air where molten rock once was, meaning it could no longer support the weight of overlying rock. The overlying rock subsequently collapsed downwards, forming a caldera. The formation of this caldera did not occur in an instant, but rather across a month, as underlying lava slowly erupted via a series of flank vents. Lava output then became intermittent until it stopped altogether. In total, about 0.15 cubic kilometers of ash had been emitted, along with 1.6 cubic kilometers of lava covering 70 square kilometers of high desert. Although the spectacular diamond craters have not erupted since, a nearby region may one day erupt again. My justification for this claim is that with the current exception of the diamond craters, all of the other young lava fields in the high lava plains occur as clusters of 2 or more closely spaced systems. Thus, while I do not expect the area encompassing the current lava flow coverage of the diamond craters to ever erupt again, there is always a future possibility of the next eruption occurring within a radius of 20 miles of the diamond crater's vents. The next eruption could be equally as explosive, damaging nearby homes and farmland and potentially disrupting regional air traffic. Yet, due to the frequency of eruptions at other clusters of lava fields in the high lava plains being as low as once every 50,000 to 100,000 years, the U.S. Geological Survey gave the diamond craters a designation as a very low-threat volcano. Today, the remnants of this spectacular eruption can be visited as part of the diamond crater's outstanding natural area. I have linked the relevant Bureau of Land Management webpage in this video's description. I hope you enjoyed this extended duration video, as I thought there was simply too much information on this volcano to fit into a single 5-minute video. During the last several years, millions of people around the world have watched the frequent and episodic effusive volcanic eruptions occur on Iceland's Reykjanes Peninsula. But what if I were to tell you that such an eruption could not only occur within a section of the United States, but actually did occur around 11,000 years ago? What I am referring to is the Devil's Garden volcanic field, which in 9000 BCE produced a 3.2-year-long eruption that resulted in 38 square miles being covered in a layer of lava which averaged 40 feet thick. And despite the fact that the vents which fed this eruption will not erupt again, the volcanic field it is a part of is still considered as active. In other words, this little-known volcanic complex may one day erupt again despite today containing no surface activity such as gas vents or hot springs. So, why exactly did the Devil's Garden volcano, which measures 6.1 miles wide and 10.8 miles long, form? The short answer is the disappearance of regional glaciers after the last glacial maximum 21,000 years ago combined with the disappearance of a 1,000 square mile Pleistocene lake 15,000 years ago. Both of these features had placed large amounts of strain on the underlying crust, causing it to sink downwards. But once this mass was removed, the crust rebounded upwards, creating numerous faults and weak points for magma to intrude into. As a result, between 20,000 and 9,000, but most notably 12,000 to 9,000 years ago, areas of the world which at one point had glacial cover saw an increase in the rate of volcanic eruptions by as high as 300%. Yet, the volcanism which formed these features indicates that they are not part of the Cascade mountain range, hence their different composition. Instead, they are part of a strange province known as the High Lava Plains, where during the last 15,000 years, repeated large outpourings of lava have occurred from multiple complexes, leading to a cluster of black lava fields so large that they are each visible from orbit. The eruptions in this province were triggered by a quirk on a specific section of a subducting tectonic plate. Although the exact reason why this occurred is unclear, in geologically recent times a small portion of the Juan Fuca plate was unexpectedly pulled downwards at a steeper angle. As a result, viscous material in the mantle was quickly forced into the empty space the recently shallower angled plate once held, creating a curved motion that pulled molten rock upwards. Fairly sizable volumes of the molten rock pulled upwards by this action subsequently intruded into the crust, some of which eventually erupted, forming the volcanoes of the high lava plains. The Devil's Garden lava field formed around 9000 BCE when a 2 kilometer or 1.24 mile long dike of magma began rising through the crust. A plume of white volcanic gases then started rising from 3 points on the ground until suddenly a fountain of lava shot several hundred feet upwards. As lava erupted, small fragments of gas-rich molten rock thrown into the air fell back to the ground largely within a 400-foot radius, building a small ash-pour volcanic cone known as a spatter cone. Eventually, the southern two spatter cones became inactive after growing to 62 feet in height. As lava flows expanded outwards, their motion was both aided by gravity as they were pulled down slope, while also blocked by higher pre-existing terrain. Eventually, the turbulence related to the main active channel crusted over, forming a lava tube. This lava tube, which is today the site of the 1/4 mile long Derrick Cave, is what more than 90% of all lava at this volcano flowed through at one point. Supplying lava to more distant locations while maintaining a high temperature, lava continued onwards, flowing up to 12 miles away. What started as stronger eruptive activity slowly declined over time, eventually becoming intermittent before stopping altogether. In total, 1.2 cubic kilometers of lava was emplaced. Due to the fact that this volcanic field's recent eruptions were all effusive or only moderately explosive, its low eruptive rate, and the fact that very few major points of infrastructure exist nearby which could be threatened by a future eruption, Devil's Garden does not rank among the nation's most dangerous volcanoes. As a result of these hazards, the U.S. Geological Survey designated Devil's Garden as a very low-threat volcano. Within eastern Oregon are a series of young lava fields so large that they are visible from orbit. These represent the products of 4 volcanic eruptions that occurred in the last 15,000 years, which led to 135.7 square miles of land being covered in a layer of basaltic lava. The youngest of these lava fields formed a mere 3,200 years ago and is today located only 18 miles west of the border of Idaho or 20 miles northwest of the community of Jordan Valley. This community is how the complex of young lava flows received its name, being known as the Jordan Craters. Here, a collapsed cinder cone, a chain of spatter cones, and a vast black lava field that contains lava tubes marks the site of recent volcanism which may have been witnessed directly by native populations. The Jordan Craters complex is a volcanic field consisting of a series of 4 separate smaller lava fields which each were fed by a single central vent. Ranging in age from 250,000 to 3,238 years old, you might be surprised to learn that each of these basaltic lava fields erupted essentially the same volume of lava, ranging from between 0.8 to 1 cubic kilometers of molten rock. In other words, the next time the Jordan Craters volcanic field erupts again, which seems to occur about once every 65,000 years, the same volume of molten rock is fairly likely to be emitted. Just so you can understand how large of a volume this is, 0.8 cubic kilometers is about 4 times the total amount of lava which Iceland's Reykjanes and Fagradalsfjall volcanoes have produced through a combination of 5 eruptions between 2021 and 2024. The most recent eruption of the Jordan Craters began around the year 1238 BCE when the upwelling of the underlying mantle due to the recent steepening of a narrow section of the subducting Wandle-Fuka tectonic plate caused a volume of magma to intrude into the crust. As this magma advanced upwards, it generated a series of progressively shallower earthquakes. Forming into the shape of a 1,400 meter or 4,590 foot long dike, it formed a fissure of that same length on the surface which began releasing gas. Finally, at the eastern end of the fissure, expanding gases propelled shallow magma upwards, creating 500-foot-tall lava fountains. Due to the height of these initial lava fountains, some magma was expanded to such a degree that it fragmented into ash, soon being deposited primarily in a 3,000-foot radius. The extent of the active fissure soon expanded to the west and east, causing a series of 13 small spatter cones to begin emitting lava at a lower rate while sending what they erupted downhill towards the east-northeast. Reaching its longest extent only a few hours into the eruption, there was even a period of several minutes where a tiny fissure erupted lava at a spot 2,600 feet west of the main lava flow edge. This westernmost vent soon ceased erupting, and as the hours progressed, several smaller spatter cones ceased erupting, sending their molten rock into larger vents. This consolidation continued until only one vent was left, which had now grown to be a 30-foot-high cinder cone. At this cinder cone, which we today call Coffee Pot Crater, intermittent explosions of ash alongside lava fountains occurred from its central vent, depositing ash in the vicinity. As these explosions were ongoing, the amount of lava in the cinder cone became so great that a temporary lava lake formed. Eventually, too much lava existed within a section of the upper cinder cone, causing it to collapse its eastern wall and spill out as a sizable flow of molten rock. This process repeated dozens, perhaps even hundreds of times, while at the same time a more sustained flow of lava occurred from its eastern flank, traveling to more distant locations via a series of lava tubes. As lava flows advanced to locations up to 10 miles away, they burnt and felled trees, one of which was at the edge of Cow Lake. A piece of this burned wood subsequently fell into the lake and was buried by advancing lava flows, only to later be unearthed several thousand years later and carbon dated to determine the age of this geologically recent eruption. The eruption likely continued for a period of 2 months until lava output ceased altogether. Lava subsequently drained away, causing the center of Coffee Pot Crater to collapse and form a crater. Although the Jordan Craters has not erupted since, it is one day likely to erupt again via a new cinder cone vent or small shield volcano. Due to this potential hazard but low rate of eruptions, the U.S. Geological Survey designated the Jordan Craters as a very low-threat volcano. What you are looking at is a large fragment of obsidian, which is a type of natural volcanic glass at an active volcano in Oregon. As we zoom out, you can see that this is not a singular isolated fragment, as this entire massive flow is littered with obsidian, hence its dark coloration. What I am standing on is the youngest eruption deposit of the Newberry volcano, specifically its 2.8 square kilometer or 1.08 square mile big obsidian lava flow, which was emplaced in the year 690 CE. In all, this 61-meter or 200-foot tall rhyolite composition lava flow contains an estimated 43 million metric tons of obsidian, since it comprises 10% of the lava flow, with the other 90% being composed of rhyolitic pumice. The eruption which formed this deposit was truly massive, equating to a Plinian eruption 1/3 the size of the 1980 eruption of Mount St. Helens, sending measurable amounts of ash all the way into Montana. This occurred due to a sustained eruption column which rose up to a height of 21 kilometers or 69,000 feet. And yet, something is quite strange. This eruption did not occur at a stratovolcano or even a lava dome complex such as California's Lassen Peak, but rather something quite uncommon in the Cascade Range, a shield volcano. Specifically, the Newberry shield volcano. Newberry is truly massive, with its main edifice and vents encompassing an area of 1,200 square miles, or a little larger than the entire land area of Rhode Island. While, yes, Newberry has produced a number of very powerful explosive eruptions, hence the big obsidian lava flow and its two-stage caldera, it is primarily composed of highly fluid basalt and basaltic andesite lava flows. These lavas during eruptions can flow at speeds of up to 30 kilometers per hour or 18.6 miles per hour and quickly cover far away areas in a layer of molten rock. For example, in the year 5050 BCE, the eruption of the lava butte cinder cone would result in the emplacement of a 9-square-mile lava field covering the outskirts of what is today the community of Deschutes River Woods, population 5,800. The reason for the combination of effusive or mildly explosive flank eruptions and highly explosive summit eruptions relates to the Newberry volcano having at least 2 separate magma chambers which each feed different types of eruptions. While this volcano as a whole has not erupted since the year 690, it has seemingly averaged at least 1 eruption per millennia during its recent geologic history. To further elaborate on this point, here are the vast areas lava and volcanic vents have covered just simply in the Holocene epoch. Since any future summit eruption could generate damaging lahars which descend Paulina Creek into the Little Deschutes River, it should come as no surprise that Newberry is classified as a very high-threat volcano. So, how exactly did such a massive shield volcano grow? Well, this is largely owed to both its high eruptive rate and old age. Newberry has erupted at a rate during its lifespan which is about 3.6 times higher than Mount Rainier or 73% higher than Mount Adams, while at the same time being a whopping 600,000 years old. Early fluid eruptions of basaltic lava transitioned into both basalt and basaltic andesite, which spread out over a large area, albeit with many vents aligned along a north-to-south trend. By 500,000 years ago, after thousands of eruptions, meaning an average of more than 1 every century for 100,000 years, the Newberry volcano reached a monstrous height of 14,000 feet above sea level. However, one of its magma chambers slowly became more and more silica-rich until it triggered a major explosive eruption 300,000 years ago, which was 19 times larger than the 1980 eruption of Mount St. Helens, causing the volcano to lose a significant amount of height and form a large caldera. This caldera would then further expand in a similarly powerful eruption 75,000 years ago, creating its modern 8-kilometer long and 5.8-kilometer wide depression in the ground, now filled with its 2 large lakes. While eruptions within this caldera have largely been rhyolitic, eruptions outside the caldera begin clustering along a north-northwest trend known as the Northwest Rift Zone. This rift zone has produced abundant purely effusive to moderately explosive eruptions in the time since, hence why the modern volcano is elongated along the rift's orientation. As a final note, I want to remind everyone that the Newberry volcano is statistically the most likely volcano to erupt next in the state of Oregon, if we are talking based on its rate of Holocene eruptions. West of the city of Bend in Oregon is a towering active volcano whose highly symmetrical edifice is currently the site of a ski resort. Known as Mount Bachelor, this fascinating volcano is younger than it looks and may one day erupt again. For example, its most recent eruption began around 6000 BCE, forming the 560-foot-tall Egan cinder cone, an event which covered 3.6 square miles in lava and started forest fires. While the towering peak of Mount Bachelor is by far the most voluminous feature, being a young stratovolcano built on top of a young shield volcano, it is not the only part of this volcanic complex, as the Mount Bachelor volcano also consists of a second shield volcano, more than a dozen cinder cones, and the remnant of a volcanic eruption which occurred underneath a thick ice sheet. Altogether, this cluster of recent volcanism covers an area of 135 square miles or 350 square kilometers, with all 50 of its vents forming between 18,000 and 8,000 years ago. The vast majority of these vents are spread out across a 15.5 mile or 25 kilometer long lineament which seemingly represents where magma from the subducting Juan de Fuca plate somewhat evenly rose. Approximately 18,000 years ago, a 1,500-foot thick glacier existed along the majority of Oregon's Cascade mountain range. It is in the eastern section of this zone where glaciers existed further east than the rest of the mountain range due to the presence of the Broken Top volcano that magma began intruding into the crust. This formed a northward trending dike 1 mile in length which, upon reaching the bottom of the glacier, produced a layer of pillow basalt which is more commonly found at deep submarine volcanoes. As 3 vents formed, they began to explosively interact with the glacial ice above, creating heavy ash emissions to produce a material known as hyaloclastite. But before these subglacial cinder cones could reach the surface of the subglacial lake they created, the eruption ended. It would be another 1,000 years before the second eruption occurred, but this time at a location 4 miles to the south. With no glaciers present overlying this patch of ground, a similar dike created a chain of 5 small cinder cones, the northwesternmost of which was the dominant vent. As intermittent explosions of ash occurred, several 100-foot-high lava fountains were generated, propelled upwards by expanding gases. During the next 5 weeks, basaltic lava expanded outwards in all directions, dividing a larger lake into the Elk Lake and Lava Lakes. With 1.8 square miles covered in fresh lava, the eruption ended. The next eruption occurred 6.5 miles to the southeast, producing the beginnings of a small shield volcano. Several eruptions occurred over the next 1,000 years, building Sheridan Mountain. Between 14,000 and 12,000 years ago, more than a dozen separate eruptions from scattered cinder cones, some of which erupted on top of Sheridan Mountain. Eruptive activity later moved further northwards and formed the Coal Butte Shield Volcano, which acted as a base that Mount Bachelor would grow on top of. Mount Bachelor proper formed due to more than a dozen eruptions between 12,000 and 10,000 years ago, depositing ash near its summit and sending lava flows down its flanks. At one point, a fairly thick glacier developed on its summit, and as it advanced, it pulverized some of the basaltic andesite lava rocks into finely grained dust. After a 2,000-year hiatus marking Bachelor's longest pause to date, the medium-sized Egan cone formed in a mildly explosive eruption 1.5 miles to the north around 6000 BCE. Since Mount Bachelor has not erupted since and has not shown any signs of life in recent years, there is a possibility that it will never erupt again. But if it were to erupt again, a cinder cone forming eruption north of its central peak would be the most likely outcome, sending lava flows up to 20 kilometers away and heavy ash emissions as far as 10 kilometers away. Since these ash emissions could disrupt regional air traffic and there are residences within this radius, the U.S. Geological Survey designated Mount Bachelor as a moderate threat volcano. Clearly visible from downtown Portland, Oregon, is the towering glacier-topped peak of the Mount Hood volcano. While today, this peak popular with skiers is fairly quiet, if you had only been here in the 18th or 19th centuries, you may have very well seen not only the eruption of lava, but also a plume of ash rising into the atmosphere. Despite the small magnitude of these eruptions, which occurred across portions of 16 separate years during the 1700s and 1800s, you may not have been completely safe even if you were, at the time, 32 miles away from the eruption site. The reasoning? Well, the evidence of destruction at this faraway location involves these dead trees which suspiciously all died in the year 1781. The reason they were killed is that they were completely buried by a wall of sediment carried by a lahar which was 14 feet higher than the mean river level or a full foot higher than its worst historical flood, only to be re-exposed by later erosion. Lahars are generated during many eruptions at Mount Hood due in part to the hot volcanic rock melting portions of its 380 million cubic meters of glacial ice. These lahars can and have swept through several regional rivers, and in fact one area the Troutdale Airport is completely built on top of and thus would be once again covered by lahars if lahars of the same severity to what occurred 1530 years ago occurred again. This means that during future eruptions, as many as 7,500 people along with additional businesses could be placed at risk. With its last eruption occurring in 1866, it should come as no surprise that Mount Hood is categorized as a very high-threat volcano, ranking as the 6th highest threat volcano in the entirety of the United States. Like all other Cascade Range volcanoes, Mount Hood exists due to the subduction of the Juan de Fuca plate underneath the North American plate, triggering partial melting which causes material to rise as magma and occasionally erupt onto the surface, forming a chain of volcanoes. Mount Hood is a fairly old volcano, with its origins being traced all the way back to 500,000 years ago. The first few dozen eruptions occurred not at a central point, but rather at a series of spaced vents across a 5-mile wide area, producing ash emissions and emplacing thick andesite lava flows which built the base of the volcano. The best exposure of one of these old lava flows can be found at Lamberson Butte. Eventually, a central vent developed and a combination of ash-rich and lava-rich eruptions followed, creating overlapping layers of volcanic rock which started to build the stratocone. This gray stratovolcano may have then grown to be as much as 10,800 feet tall, but then something catastrophic occurred 100,000 years ago. Around that time, a major collapse occurred, destroying the summit and much of the northern flank of the volcano, generating a large-scale debris avalanche. Across the next 70,000 years, moderately explosive eruptions refilled this collapse scar, rebuilding the volcano to its prior height. In the time since, both andesite and dacite lava domes have erupted at Mount Hood's summit, growing the height of the overall volcano and releasing pyroclastic flows during eruptions due to periodic collapses of the growing dome. Around 5700 BCE, a basaltic andesite cinder cone erupted north of Mount Hood's summit, emplacing the tall Parkdale lava flow. A major eruptive period occurred 1500 years ago involving two multi-decade-long eruptions. These once again generated lava domes, and their occasional collapses generated pyroclastic flows which traveled as much as 7.5 miles or 12 kilometers distant. During this period, a portion of Mount Hood's southern edifice collapsed, forming the modern scar which subsequent eruptions would occur within. Its modern dacite crater rock lava dome formed during a 1781 to 1793 eruption, although this region would erupt again in 1859 and from 1865 to 1866. Mount Hood's eruptions are dominated by eruptive periods where decades to centuries of frequent eruptions occur only to be followed by centuries to up to more than 10,000 years of no eruptions occurring. It currently appears that Mount Hood is in another quiet period since its last eruption in 1866, but this could unexpectedly change in the future. Within the state of Oregon, the state's tallest peak, Mount Hood, is well known to be an active volcano. After all, its last eruption occurred in 1866, which is not very long ago. Yet, few people realize that the state's second tallest peak is also an active volcano, as 50 miles south of Mount Hood, the towering glacier-covered edifice of Mount Jefferson comes into view. Despite being heavily glacially dissected, this volcano has actually erupted 3 times since the end of the last ice age, the last of which occurred a mere 1,000 years ago. In other words, while potentially being a dying volcano, Mount Jefferson is still active and likely to one day erupt again. When we refer to Mount Jefferson, we do not only mean the peak which bears its name. The stratocone of Mount Jefferson is merely the northernmost feature along an 11-mile long and 5-mile wide stretch of land which to the south contains scattered lava domes, formerly subglacial vents in cinder cones which erupted once and then never erupted again. It is in this southern region that all three Holocene epoch eruptions occurred, occurring at three cinder cones which altogether covered 8.16 square miles in a layer of fresh-looking basaltic andesite lava. It is in this very region where Mount Jefferson's next volcanic eruption is most likely to occur, probably forming another cinder cone. Looking to the north, Mount Jefferson's towering edifice correctly looks quite old simply due to the level of erosion it has experienced. This edifice has not erupted for 15,000 years, with its origin being traced back to a time 280,000 years ago. Heading back to the Middle Pleistocene period, a sizable portion of melt created by a subducting tectonic plate began clustering at a new location which would act as a dominant vent. As andesite composition magma rose through the crust, it created an intense swarm of earthquakes. Then, reaching the surface, it produced a powerful explosion, carving out a 1,000-foot wide crater in the ground. As ash emissions were produced by Volcanic explosions along with pyroclastic flows, Jefferson's first lava flow simultaneously expanded outwards. Subsequent eruptions were similarly explosive and across the next 50,000 years would build up what is now the southern and western portion of the mountain. Some of these eruptions emplaced voluminous dacite lava domes such as what is today known as Goat Peak. Just like at Mount St. Helens, eruptions at Mount Jefferson largely occurred across periods where dozens of eruptions would occur only to be followed by thousands of years of no activity. As the main volcanic cone continued to grow, two Plinian eruptions occurred 75,000 years ago, which both sent a layer of ash to Idaho's town of Orco, a whopping 430 miles distant. This eruption wiped out all life in at least a 5-mile radius and caused more than 3 feet thick of ash to fall on Mount Jefferson's edifice. Continued eruptions during the next 60,000 years constructed the upper 3,000 feet of the mountain, with the last additions occurring 15,000 years ago. The last eruption occurred around the same time that a tall cinder cone formed on a hill on a ridge to the south, creating a lava field at what is today known as South Cinder Peak. 6,500 years ago, the first of what would become 3 young cinder cones erupted, sending lava fountains to a height of 1,000 feet, which subsequently fell back to the ground. Over the next several weeks, blocky 25 to 200 foot high lava flows flowed down glacially carved valleys to the east, largely filling significant sections of them until the eruption ended. Approximately 100 years later, another eruption occurred 2 miles to the southwest, forming the Forked Butte Cinder Cone and another several square mile lava field. The most recent eruption occurred around the year 1000, forming the South Cinder Peak Cone and creating a 0.95 square mile lava field. Each of these recent eruptions has sent lava no further than 7 miles from an erupting vent. Yet, the main threat Mount Jefferson could pose involves what would ever happen if its main cone erupted again. Any future eruption from its main cone could potentially generate pyroclastic flows, but also likely melt large sections of its glaciers, generating destructive lahars which could wipe away buildings and threaten up to 15,000 people as far as 50 miles distant. Yet, it is unknown whether the summit region of Mount Jefferson will ever erupt again. As a result of these hazards, the U.S. Geological Survey designated Mount Jefferson as a low-threat volcano. If you were on US Route 20 heading northwest of the town of Bend, you would encounter 2 fascinating volcanic features. One of these features is part of a subglacial volcanic complex involving the flat-topped Hog Rock, which is a small-scale example of a toya that completely formed underneath a thick ice sheet approximately 80,000 years ago. Yet, since this and its neighboring Hayrick Butte toya to the south have not erupted since the end of the last ice age, this complex, which I will simply call the 2 toyas, would not be classified as active but rather dormant. The same, however, cannot be said of the second volcanic feature on this trip, a partially quarried cinder cone which has hues of reddish-brown to it, being known as the Little Nash Crater. This cinder cone formed in a moderately explosive eruption in the year 50 CE, but was not alone when it erupted. As at the same time Little Nash Cone was erupting, a second cinder cone and 2 hidden vents were also ejecting lava. And if you go further south, you would encounter cinder cone after cinder cone which are suspiciously all aligned in a straight line. All of these vents, 42 in total in fact, of which 23 are cinder cones, are part of a little-known fascinating volcanic field known as the Sand Mountain Volcanic Field. This volcanic field is active and is shown by its multiple eruptions in the last 10,000 years may one day erupt again. The Sand Mountain Volcanic Field stretches across a 5-mile wide and 8.5-mile long stretch of ground west and northwest of the extinct Mount Washington shield volcano. Everything you see in this field completely formed in the last 10,000 years, including the 76 square kilometers or 29.3 square miles its lava flows have covered during that time span. Almost all of the vents in the Sand Mountain field are constrained by a series of 2 northward trending lineaments representing what once were large magma dikes that intrude into the crust. Yet, of the 42 vents, there is a singular vent which stands out, being known as the Jack Pine Cone. As shown by how heavily vegetated this cinder cone is, it may not come as a surprise that Jack Pine is also the single oldest vent in the field. If it ever produced any lava flows, they are no longer visible as they were buried by subsequent eruptions from other vents. The Jack Pine vent formed in approximately 5000 BCE just after the Belknap crater volcano produced an eruption to the south. This eruption began as a volume of unusual composition magma, aka basaltic trachy andesite, reached the surface and erupted in an explosive manner. The relevant magma was unusually gas and volatile rich due in part to its high viscosity, causing a violent Strombolian eruption to occur which may have lasted for 1 to 2 months. After this eruption ended, no further activity would occur for another 4,000 years. Then, during a time period of less than 40 years, the bulk of the volcanic field rapidly formed, involving more than a dozen cinder cones. We are currently unsure if these all erupted in a single prolonged year-long eruption or if they formed across 13 separate eruptions across several decades. I am assuming the former is correct, which occurred when a 5.9-mile-long magma dike intruded into the crust. Initially, the entire length of the fissure erupted in 1000 BCE, which would have been a spectacular sight to behold. However, as time progressed, smaller portions of the fissure became dominant, and these sites would become the site of future cinder cones. Because the area was heavily saturated with groundwater, the eruption which occurred was unusually explosive and ash-rich, even involving a subplinian phase at one point. Heavy ash emissions occurred as a result, and by the time this eruption ended, 22 square miles were covered in basaltic and basaltic andesite lava, and 0.2 cubic kilometers of ash had been ejected. This eruption seemingly created a secondary trend to the northwest, which would be the site of Sand Mountain's most recent eruption in the year 50 CE. This 50 CE eruption was an order of magnitude less explosive than the prior sequence, and through the construction of the Nash and Little Nash cinder cones covered 8.6 square miles in a layer of basaltic andesite lava. Due in part to how sparsely populated the immediate surrounding area is, the U.S. Geological Survey designated the Sand Mountain Volcanic Field as a very low-threat volcano. Right now, an intrusion of magma is ongoing at a well-known volcano in Oregon. This is occurring approximately 26 miles west of the city of Bend, where, at a section of the Three Sisters volcano, molten rock is accumulating underground at a depth of 6 kilometers or 4 miles. As a result, the magma has pushed upwards overlying ground through displacement, resulting in the ground rising by approximately 12 inches or 30 centimeters since it began. Yet, it is not a completely new phenomena, with ongoing, albeit variable uplift being detected since 1995, with the current rate of uplift being lower than it was in prior years. Since then, approximately 100 million cubic meters of magma has accumulated underground, presumably with a basaltic composition. This composition is somewhat of a good news, as basaltic eruptions at Three Sisters, which has produced everything from basalt to rhyolite, tend to result in the least explosive of eruptions. So, is a basaltic cinder cone forming eruption in the near future of this volcano? While technically possible, it is probably not. About 3 million cubic meters of magma intrudes underneath the aforementioned spot every year, but since it was first detected, it has not progressed any further upwards. And, based on the elevated detection of chloride ions in the streams around the uplift center, it suggests that repeated intrusions have likely been occurring in the same area, albeit previously undetected for at least the last several hundred years. Since no eruptions occurred during that time span, the Three Sisters complex is unlikely to erupt during the current intrusion. Besides, to reach a volume of equal to the amount of magma involved in its last eruption would take another 51 years at this rate. As the name of this highly scenic active volcano implies, the Three Sisters complex comprises three separate stratovolcanoes of differing ages, which formed from overlapping layers of lava and ash in place during explosive eruptions. There is the basaltic andesite composition North Sister, which is 120,000 to 55,000 years old, the basaltic andesite to dacite Middle Sister, which is 40,000 to 14,000 years old, and the andesite to rhyolite South Sister, which is 50,000 to 2,000 years old. These medium-sized stratovolcanoes each produce numerous explosive eruptions during their lifespans, yet a true eruption from any of their summits has not occurred in a whopping 19,000 years. Instead, in the time since, every single eruption has occurred further down the flanks of or even outside of the edifice of each stratovolcano. In the Holocene epoch, this has occurred both north and west of the North Sister and southeast of the South Sister. These eruptions had differing levels of explosiveness, and their lava flows had varying compositions and thicknesses. The last such eruption occurred around the year 500, emplacing an andesite lava flow which covered an area of 3.75 square miles and a moderately explosive eruption. While this more common cinder cone-forming eruption produced moderate ashfall and forest fires, a second common type of eruption at this complex produces dacite and rhyolite lava domes in highly explosive eruptions. These latter eruptions frequently generate destructive pyrocaustic flows, large explosions, heavy ashfall, and lahars. Since any future eruption will be likely to disrupt regional air traffic, and since approximately 7,700 people live in lahar hazard zones of this volcano, it should come as no surprise that Three Sisters is classified as a very high-threat volcano. With 7 eruptions in the Holocene epoch and a similar number of eruptions in the prior 10,000 years, it is safe to say that the Three Sisters complex erupts about once every 1,500 years on average. And now, I want to highlight a few interesting eruptions from this complex. One notable eruption which occurred 38,000 years ago west of the North Sister and placed large amounts of obsidian that were later used by several groups of Native Americans. At the Middle Sister, its last eruption 14,000 years ago and placed this thick dacite lava flow easily visible on the ground. North of the North Sister, a near-perfect north-to-south chain of eruptions emplaced more than a dozen cinder cones and craters between 60,000 and 20,000 years ago. Finally, on the southern outskirts of the South Sister, a major explosive eruption that rated on the Volcanic Explosivity Index as a 4, or about 1/10 the size of the 1980 eruption of Mount St. Helens, and placed a large and an up to 650-foot thick rhyolite lava flow.